everybody. I hope you guys enjoyed doing that exploratory lab on the properties of water. I also hope that you're treating this sub as a guest in our building, because that's what these people are when they come into our building, and they help teachers go to conferences, and they cover our classes when we're gone, when we're sick. And so I hope that you are treating them respectfully so that they actually want to come back, and we actually have substitutes working for us here at our school. All right, now we're going to talk a little bit about the properties of water. Sorry, trying to get rid of that error message on my screen. All right, so if we look at the planet of Earth, it looks like a water planet. But in reality, there's just a small, thin covering of water over our surface. If we want to look at how much water there is compared to how large the planet is and how much rock there actually is on the planet. But that being said, 71% of our surface, 71%, that's almost 3/4% of our surface is covered in water. But not all of that water is something that we can directly use, we can directly drink. Not all of it is something that we can give to our animals, give to our livestock, and put on our crops in our farms. So we're going to talk today about where the water is on our Earth, how much percent we have in each reservoir. Reservoir is a word kind of meaning like container, where we're holding water on the planet. And then we're going to ultimately calculate how much water is directly available without having to be cleaned, without having to be processed for human use here on our planet. So what you're going to need is you're going to need a computer, you're going to need a calculator, you're going to need a data table, which is available for you in the Canvas assessment. You're going to need a scratch piece of paper and preferably something to write with. It doesn't have to be a pencil. It just has to be something you can write with. And then knowledge on how to create percents, which I'm going to walk you through in a second, and a protractor. So in a second, I'm going to have you get up. Everybody's going to need a computer, calculator, scratch piece of paper. If you don't have one, there's some available on the left-hand side of the room. And then we won't use a protractor in this activity, but we're going to need it later, so I'm going to have you get it there at that time as well. Now, before you get up, 7th period. I know there's a million of you in this class. There's not computers for everybody. So if a few of you could use your cell phones, this activity won't be too bad on the cell phone. If you have one of those larger cell phones, that would be great if you could volunteer that so that there's enough computers available for everyone. We won't be typing. There's one question you have to answer with words, but it's not too bad. So most of it will just be numbers. Okay, so everybody go up and get the 4 things: computer, calculator, scratch paper, protractor. Pause the video, go now. All right, we're going to talk about how to calculate a percent. I know all of you were taught this, but it's been like since 3rd grade, and everybody forgot except for like 5 of you in the class today. So we're going to cover it real quick again. So whenever we're calculating a percent actually means parts of 100. And so whenever we're doing this, we're going to take a ratio, and we're going to transfer that into 100 parts, or the parts of it is that makes up 100. So whenever we get a percent, we're seeing how much it is out of 100%. All right, so what you need to calculate a percent is you need 2 things, basically. You need how much you have, and you need how much there is that's possible. So let's work with an example that we are used to. Let's say you have taken an exam, and on that exam, there are a total of 35 questions. Now let's say you studied really hard on this test and you studied the wrong material, and so you actually didn't do very well. So let's say you only got 20 questions correct. So that's what we have. So the amount we have or what we got on the test is we got 20 questions correct. All right, so calculating a percent is a simple ratio. We are going to take how many we got, so 20 questions, how many got correct, how many we have, and we are going to divide by the total amount possible. So here I have my fraction or my ratio of how many questions I got correct, how much I have, divided by the total possible amount here. Now, the next step is to sort of translate that into parts of 100. And we're going to do that by multiplying it by 100. Whoops, not 1,000. Don't multiply it by 1,000. It will be wrong. Oh my gosh. Okay. It's going to be okay. Concussion. Okay. So, 20 questions divided by 35 questions. So what we have, what we got, divided by the total, multiplied by 100, and then we're going to have the equal sign. But let's run through how to put that into the calculator so that it comes out right, because some of you are going to put this in the calculator and it's going to be just fine. It's going to come out with the right answer. And some of you are going to put this in the calculator and it's going to end up making 20 divided by 3,500. So whenever you're using a calculator, it's always great to be safe, because you don't know how your calculator maybe works specifically, to use parentheses. Yeah, I know these are gimpy. Don't make fun of me. Okay. So I'm going to put parentheses around my ratio here, and then I'm going to multiply by 100. Let's see what that looks like on a calculator. So I've got my trusty Calc-key here. Oops, my bad. Undo. Whoop. All right, trusty Calc-key here. So here on my calculator, I've got my percent symbols down here. If you're using your calculator on your phone, you might actually just turn the calculator sideways. Most calculators, when you do that, you'll see all these other options that I have up here, as including these parentheses. They're usually going to be over here on the top to the left of your calculator, and you'll have your pad over here, but whatever, that doesn't matter. All right, so what you do to type it in the calculator, and everybody do this with me as we're going so that you're used to you doing it and having it work well, is you're going to open calculator by hitting the open paren or open parenthesis. You're going to type in your number 20. You're going to hit the division symbol, which remarkably looks a lot like a fraction, with the first dot being the numerator and the bottom dot being the denominator. What? You're going to hit that button, divide. You're going to type in our total amount, our 35. You're going to end paren. And then you're going to multiply by 100. I can't multiply by 100. I got my thing in the way. Multiply by 100. All right. Now, a lot of you have this need to give me every decimal that ever existed on the planet. But today, I'm not going to explain to you how or why you should use certain decimals. I'm just going to tell you whatever the question asks you to, whatever decimal place or whole number the question asks you to round to today, that's what you're going to round to. And you're not going to do any other weird, like, give me every number on the calculator. Don't do that. I don't want that. Oh, that's cool. Look, it repeats. 142857. 142857. Okay, that's just cool. Anyway. All right, so our answer here is going to be 57%, because I just want you to give me this. In this case, I'm going to have you give me just the percent, not anything in the decimal here. So 57%, and we're just going to write that as 57 and percent symbol. That percent symbol actually tells us that this number in reality is 0.57, but it's okay if you don't understand that right now. It's not important for our assessment here. Now, on the Canvas assessment, it's not going to let you put the percent symbol, and that's going to bother some of you, because it's just going to ask you what percent it is, and you're just going to put in the number 57, or whatever number it is that we're calculating. Now, some of you are going to struggle with this assignment because the numbers are really, really big. We're talking in the millions, and I think one number might be in the billions. I'm not sure. I can't remember. But just calm down. It's going to be okay. All right, so let's do another example real quick, because there's going to be something harder in the assignment than just a simple percent. I hope all of you have something like this written down so that you're taking notes and so you can reference them again when you're actually doing the assignment. Okay, so let's say we have another question where we have a bunch of numbers. So let's say I need to figure out how many marbles are blue. That sounds like a typical math problem. Great. But I have a bunch of different colors of blue. So I've got... So let's say I have 1 teal marble. I've got 24 aquamarine marbles, 19 blue marbles, and then 9 navy marbles. Wow, that's hard for me to say. And so I know some of you are thinking right now, I doubt Mrs. Grether has any of her marbles, but we're going to go and see all these blue marbles that I have. So we're going to go ahead and we're going to add up the total first, because we want to know what percent we have of blue marbles of our total. So first we have to find the sum. Now remember that a sum is just basically adding up all of our marbles here in this case. So to do this problem, the first thing that we're going to do is we are going to add up all these blue marbles. Right, so I'm going to go ahead and make a line here and section this part off because we don't want to look at this anymore. That was a terrible line. There, much better. Okay, so first we're going to calculate a sum of all of my blue marbles. So the first thing I'm going to do is I'm going to say 1 plus 24 plus 19 plus 9. And those of you who maybe didn't see how I got those numbers, I have 1 teal, I have 24 aquamarine, 19 blue, and 9 navy. So I found my sum, which is 53. And let's say the total number of marbles that I have is 52. 53 apparently is what I typed. So 53. Just kidding, that's the number we have already. So let's say I have 102. Great. So I have 102 marbles. I want to see what percent of my marbles are blue. Alright, so I'm going to take my trusted calculator. I'm going to take 53, because that's how many I have of my total. So I'm going to do parenthesis, 53. I'm going to divide that by my total, 102. I'm going to end parenthesis. Make sure you're doing this on the calculator with me. Make sure you're getting the same numbers. If you're not, ask for help. And then we're going to multiply that by 100. We're going to hit equal sign. Alright, so that gives me 51%. But I don't just have 51%. I got 51.96, yada, 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 yada. So if I'm asking you for just a whole number, if I just want a whole number and I say I need a whole number, we're going to round to this number here, the ones place. Now let's go ahead and write this number down. I'm going to write down a few digits here so that we can look at this number. Alright, so we've got this number 51.96078. That's our full number. But what we want to do is we want to round to the nearest whole number. So we don't want all of these digits here. So what we're going to do is we are going to focus our attention on this digit here because it's the next to the one, directly next to the one to the right of the one that we want to look at, we want to round with. So because we're rounding to the ones place, we're going to look at this number right here. Alright, so rounding rules. You might want to write these down so you can remember them if you don't remember rounding rules. So our first rounding rule, you're going to look at the number directly to the right of the number you want to be rounding. So for now we want to go to the ones place, and it happens to be a 1. We're going to look to the right of the number we want to round to. So we're going to look at this 10th digit, this first decimal. The second rule is if the digit, sorry, how to fix that mistake. The second rule is if the digit is 4 or lower, we're going to round down, or basically just remove it. So if this digit right here, if this 10th digit, if this was the number 43210, we would actually just remove these decimals completely as if they didn't exist and they didn't count and they didn't matter in the world here. And so our answer would just be 51. Is if the digit is 5 or higher, we're going to round up. And that means we're going to add 1 to our digit that we're rounding. So what that is going to look like, let me grab my red pen here, is remember we are rounding to this digit here. We want to round to the next whole number. So we want to round to the ones place. So we're going to look at our tenths place. And it says TENTH place. So the tenths place. And if this number is 5, 6, 7, 8, or 9, we are going to add 1 number to our ones place. So we're gonna add 1 to this spot. This 1 to a 2. Sorry, change this 1 to a 2, and then again, we're going to get rid of the rest of the decimal. So if we're rounding this one properly, it's not going to be 51, but instead our answer will be 52%. Now in Canvas, you guys already know this, but if you don't put the answer in exactly how it needs to be, it won't accept it as correct, right? And you're going to get it wrong, and it's going to hurt your feelings and hurt your soul. So make sure you're rounding correctly. Make sure you're putting the answer in exactly how it's asking. A lot of the times it's going to ask for you the first decimal place or the third decimal place. Make sure you're paying attention to what the question is asking you, what it's asking you to put it into, and you're rounding properly. Now, if you need help rounding, work with the person next to you. And by work with the person next to you, I don't mean talk and chat with the person next to you. I mean ask them for help. Are you doing this right? What did you get for your number? And I also don't mean have the person next to you do the math for you and then have you just put it in. Don't be lazy. Actually learn. Make your brain awesome. Make your brain grow. And everybody do this exercise and everybody work at it. All right, so we're going to give you some time to get this completed. And then when you're done with the Canvas activity, we're going to go ahead and go back to taking notes. All right, so what we're going to do, everybody on your computers. Boop, hold on one second. Okay, everybody open up your computers. Remember, on my computers, always, 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 you are going to browse as guest. So go to dsd.instructure.com. That's dsd.instructure.com. Or you can go to the school's webpage and you can click the login, and then it will reroute you and take you to where you need to go. All right, if it happens to take you actually to DSD Canvas, let me log out so you can see what that screen looks like. If it happens to not bring you to the Microsoft page, so it looks something more like this, and this can happen sometimes. Some of you magically bypass the system and Microsoft doesn't reroute you. So if you happen to get here, you're going to type in your email address just like normal, but your password is going to be different. So if you happen to see this screen where you've got DSD and it looks like this blue screen, you're going to type in the first letter of your name capitalized. So let's say my name's Cassie. My name would be capital C for my password. And then it's going to be your PIN number that you have for school. So again, that would be the capital of your first given name. So if you go by, let's say, Gabe, but your name is really David, so you would go capital D and then your PIN number. Now again, if you're in Microsoft, you're not going to do that. You're just going to put in your PIN number like you always do, and you're just going to enter that. Okay, so go ahead and go into Canvas. All right. Don't show me this again. Don't put that on your computer. Don't put no. Put no on your computer. I'm going to put yes on mine. I don't know why it changed. Okay. Once you're here, you're going to go to Earth Science. You are going to collapse this 8th grade review module, which most of you already have. You are going to collapse this experimentation module, which most of you have not. So collapse that. And then you are going to see standard coursework, how much water is there part 1 of 2, and how much water is there part 2 of 2? Yes, there's 2 assignments. I know a lot of you freak out when I do this, when I split it up into multiple assignments. But the first assignment is just 1 question. Because here's the thing, if you mess up the first question, everything you do on the whole assignment will be wrong. So what I did is I made the assignment with just question 1 on there as 1 assignment. And then once you get it right, then write that number down and move on. So the first question, let's go ahead and click on it. Let me zoom in so you can see what I'm doing. Let me actually preview in student view because this one I actually have a student view. What? Okay. So when you come here to this assignment, it says, in this assessment, you will need to enter numbers exactly how they are requested or your answers will come up wrong. Make sure to round properly. Remember when rounding, you look at the digit to the right of the number of the one you are keeping. If the number is 5 or above, you round up, adding 1 digit to the one you're keeping. If the number is 4 or below, round down, leaving the digit you are keeping alone. To calculate a percent, add up all the numbers that you have, divide the number in question by the total, which is the sum, that you already calculated, then multiply by your result by 100%, or 100, sorry, not 100%. All right, now this gray stuff, ignore it. It is in Spanish unless you need Espanol to be able to read and function properly. So that's not for you. Don't translate the page or it will screw everything up. Trust me. Okay, so question number 1. It gives you this massive data table with these huge numbers. Don't freak out. It's still the same as we did in our examples. What it's going to ask you to do, it says we need to find out how much water on Earth is in different reservoirs and how much of that water, percent-wise, is available for direct human use. Below is a data table that shows our best estimates for how much water is in each location. That's written wrong. Water is estimated in the volume measurement of cubic kilometers. Your first step will be to calculate how much water is on Earth. Find the sum of all the numbers in the below table. Enter it as your response and then use this number for all of the following equations. Just to make sure your number is correct, submit this assessment to ensure your number is correct before moving on to part 2. Do not round your answer. Just enter it as it appears on your calculator. Alright, so this number, all you're going to do on this one is you're just literally going to add up all of these numbers. And then once you have the total, you're going to hit enter on your calculator, and then you're going to write down your number here. Don't write with letters. That's wrong. All right, so let's say this is the answer. It's not the answer. Don't put this as your answer. It's not the answer. All right, so here I've got commas. It doesn't like commas. Canvas is like, don't put the commas in there, so I'm going to remove the commas. And then once you submit the quiz, it's going to tell you whether or not your answer is correct. All right, when you scroll down, you're going to look here and it's going to say incorrect. And surprise, it's not going to tell you the right number. Once you get the right answer and you get this correct, you're going to write down your result, whatever the correct number is, so that you can use that in all of your calculations, because this will be your total of water that you're going to calculate all of your reservoirs from. All right. Go ahead. Once you finish that, you're going to hit the next button. Let me move this out of the way. Next button. And you've got that number right. And you're going to go ahead and attempt part 2 of 2. Go ahead. Work on that now. You got about 20-ish minutes or less to get that done. There's only 6 questions. So this should be 10 minutes. This should take you 10 minutes or less. All right. Mark, get set, go. All right, go ahead and push pause now. All right, so now that we have done this activity, hopefully most of you got that really well, we are going to create a pie chart or a pie graph using the data and your protractor. So I'm going to show you. You don't need to use your calculator and calculate these numbers, but I'm just going to briefly show you how to create a pie chart based on numbers that you have, parts of a whole. because remember, that's why we're using pie charts. When we have a total of something and all of the things that we have add up to one whole thing, one whole pie. All right, so what we're going to do first is you are going to go to your notes. So everybody pull out your notes, and in your notes we are at the start here on page 15. So everybody pull out your notes, something to write with, and turn to page 15. Now that means everybody, not just everybody who actually does it because they want to learn and they want to retain this information and they want to do well. Everybody, even those of you who always try to pretend like I don't notice that you didn't pull your notes out, you pull your notes out too. Okay, so what we're going to do right here, we are going to create a nice circle there because we are going to create a pie chart of this data here. We discovered, or you should have discovered, that almost all of our water is actually in the oceans, which makes sense. They're really big. They're covering most of the planet, but about 96.5% of all of our water sits in the oceans. About 2% is frozen in Antarctica and on the Greenland ice sheet. And we call this part the cryosphere. Now, cryosphere would technically be part of the hydrosphere. It's just the frozen water. And yeah, we also have alpine glaciers in the mountain. We also have snow in other places, depending on the time of year, in different places on the planet. And we have ice on lakes and rivers and that kind of stuff too. But that's such a small amount. And that's going to be actually counted in our all other water, along with our permafrost. So when we're talking about this cryosphere ice, this 1.7%, we're actually mainly talking about the massive ice sheets that exist on our planet in Greenland and Antarctica, like I already said. And then about 2% of that is also going to be locked up in groundwater. Again, that's not water on the ground, but it's water in the ground. Water of the groundwater. All right, so go ahead and do this. We're going to, right here in our notes, make a nice fine circle. So go ahead and make your circle more on the left side of this section than the right, because we're going to write some stuff over here. So I'm going to actually move mine over. Okay, there we go. All right, now I'm going to show you how to actually make a proper to the line exact pie chart. And it all starts with being in the middle of your pie chart. So go right to the middle center of your pie chart if you want to be perfect, because you're just that kind of person who's just awesomely perfect. You can take your protractor. At the bottom of your protractor actually is a ruler. You're going to measure the distance, measure the diameter of the circle, and go ahead and place out your dot right in the perfect center. I'm not as much of a perfectionist, so I'm just going to put my dot where it looks like about the middle. That's going to drive some of you crazy, but that's okay. All right, now we're going to make a straight line as straight as you can. You have a protractor, so you can actually make a straight line. Not so much. So I'm going to draw a gimpy line as best as I can straight out to the edge of my circle. Boop, not horrible. And so that's going to be our starting point. So now what we're going to do is we are going to calculate how much of our circle, how many degrees of our circle we should have for 96.5%. Now, all of you should know from math that a circle is how many degrees? Think in your head, or you can say out loud in the classroom if you're the smarty pants and you remember. Every circle has 360 degrees. That's why when we jump in the air and we spin all the way back around, we call it a 360. It's because we've turned an entire full circle. So here in our trusty calculator, you don't have to get your calculator out. I'm going to go ahead and get mine out. Here in our trusty calculator, I am going to take my percent, my 96.5%. And if you had a percent symbol on your calculator, you could hit that and turn this back into a decimal where it should be, but I don't have that percent symbol on here. So instead, I'm going to divide my 96.5 by 100. So I don't have percent, but I actually have the numerical representation that 96% represents. So I've got parts of my whole here. So I've got 96.5 or 0.965 as my number. So that's my percent, and I'm going to multiply that by how many degrees there are in a circle. So every percent, you're just going to times it by 360, and it will tell you how many degrees your percent represents. So right here, 96.5% represents 347.4 degrees. Now, if we were being uber precise, we'd actually do that 0.4, but we're going to just estimate. All right, so how you're going to do this, instead of me measuring 347 degrees all the way around, because my protractor ain't a circle, it's at 180, it only has 180 degrees, what I'm actually going to do is I'm going to find out how much this space is that's left over. So because all of this is going to be my 96.5%, that's my 347 degrees. But I'm going to say, I'd rather try to just graph out or mark out what the remainder is. So I'm actually going to take my number, my ocean's number, and I'm going to subtract that from 360. 360 meaning all the degrees of my circle. And so that's going to say 12.6%. So I have about 13%. So what I'm going to do is you are going to take your protractor. And because I don't actually have a protractor on the computer here, I'm going to draw myself the most beautiful protractor you have ever seen. Actually, and I'm going to do it in orange, not black, so you can see it a little bit better and it won't be messy with what I'm doing here. Alright, so here's my protractor, and I know what you're thinking. You're looking at that and you're like, wow, Mrs. Grether, that is the most impressive protractor I've ever seen anyone draw. And you would be right. So what you're going to do is you're going to take your protractor, and your protractor has a little hole in it, and it has almost a little crosshair, as long as it's not old and been rubbed off over time. But there should be a hole and a little crosshair. You're going to line that up with this beautiful line that you made earlier on your circle, and that hole is going to be right over top of that center of the circle, that dot that you made earlier. So you're going to line it up with our starting line here. And since we calculated that our degrees left over were 12.6 degrees, that is the degrees we are going to measure here on our pie chart. So what you're going to do is you are going to take your eye, you're going to look at this, you're going to go from the center point and you're going to extend out. You might need a piece of paper or something to line it up, and you're going to extend it out to about where 12.6 is. So this line should be lined up with your 0, and then this line should be lined up with 12.6. So right here I got 10, I can see that goes about here, and then I've got my 15 and my 20. 15's about there. So I'm going to eyeball the best I can where 12% is, because, well, I don't actually have something very good here. And so I'm going to take my line from here all the way back to my center. Make a straight line. Don't make a I've been spinning around too often and then I try to walk straight kind of line like I just did. You make your line straight. You have a protractor. You can make that line perfectly straight. So eyeball it. Say, okay, it's about right here. Use a paper to line it up. Connecting it with from here all the way to your 12.6, and then make a mark and draw your straight line. Alright, so when you're done with that, it should look something like this. I'm going to go ahead and color this part in blue because color makes the world beautiful. You can color yours anytime you want, any color you want. It doesn't have to be blue, or you can not color at all and be that kind of person. Alright, so there is a lovely, beautiful coloring. I know you're thinking it looks like a kindergartner just did that with their eyes closed, but you would be wrong. Alright, so we're going to go ahead and label this section. We're going to label this section Oceans. So we'll label this Oceans, and we're going to put down the oceans have 90, it's about 97, but we're going to put 96.5%. So of the water on our planet, of all the 100%, 96.5 exists in our oceans. All right, next step, we need to calculate how much of our oceans is trapped up in the cryosphere, or at least in our ice caps. So what you're going to do is that number was 1.7. So we're going to take 1.7, not 17. We're going to take 1.7, and we are going to divide it by 100. So we can take it back into our decimal form. And then we're going to multiply that by 360 degrees, the degrees of a circle. And that gives us 6.12, basically 6 degrees. If we had a bigger circle, it would be better to go all to that 1 point, but we have a very small circle, so like the width of our pencil is going to be like 0.1, so it's not going to matter. All right, so let's go ahead. You're going to pull up your protractor again. Go ahead and put your protractor on your paper. Yeah, so I've got my protractor here, and I know what you're thinking. You're thinking, wow, that's even better than the first time. How are you this good at drawing? And you would be right. All right, so again, maybe your crosshairs need to be lined up right here in the center dot. You need to have your 0 mark on your line, so it's lined up perfectly with line. It's lined up perfectly with 0. And we are going to take and we're going to make a mark at about 6-ish%. So here's my 5, and then my 6 is like just a little bit beyond that. And so it's going to be about in the middle of what we've previously drawn. Go ahead, make a mark, and then line it up with the ruler and make yourself a perfectly straight line. All right, here we actually have 3 different sections. I'm going to color this one in with yellow expertly. And then I'm going to choose pink. I don't know. It doesn't matter what color these are. It just matters that they're different. Or if you're lame and you just don't have any color because you just don't want to have fun in life, then you can have whatever you want. All right, so we're going to go ahead and label these 3. So I'm going to put a line coming out here because this is too small for me to write in there. So I'm going to put line there, and then this third one is our last number, which is so small that even our pen stroke would be too thick. So we're just going to indicate that by a line coming off this line here. All right, let's go ahead and label this top one. We're going to label this one the cryosphere, or actually you don't need to know that term, so let's just label it ice. So we'll label ice, and this is 1.7%. Let's go ahead and label our second one here. We're going to label this groundwater. Remember, water in the ground, not on top of the ground, at groundwater. And then our third one here, bloop, bloop, we're going to say all other water. So all other water on Earth, bloop, 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 on Earth, one more time. And that is going to be represented by our decimal fraction, well, right here. So very, 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 very little. This all over the Earth, all other water on Earth, that is going to include our river water, all of our lakes, all of the water in the atmosphere, all of the water that's locked up in biological organisms in your body, in their dog's body, inside of trees. All of that water is represented by this tiny fraction of all the water left over on Earth. All right, now that we've made that pie chart, the take-home messages here. So we've got all this in the ocean, can't drink that, can't use that without processing. This water, most of it is ice. We could totally melt it, but it's locked up away where people don't live, so it's not very useful. This groundwater, most of this groundwater, well, not most of the groundwater, but more than half of the groundwater is either saline, which is a word that means salt water, or it is polluted because we polluted the ground surface, and then the water actually, as it rained, percolated through percolated through the ground into the aquifers and brought that pollution down with it. And so actually, and even a small amount of this groundwater is so deep that we actually haven't even been able to drill deep enough to reach it. So all of the water we have, there isn't actually very much accessible for us for direct use, for feeding to our animals, for feeding our crops. That's right, feeding our crops, because feed it with water. Just ignore that I said that wrong. And for drinking, for direct human use without lots of processing and a lot of energy going into it. So our take-home message definitely here is this. All right, write this down on your notes. You got this place right here on your notes where we just made our pie chart. You've got 1, 2, 3, and 4 bullets here. Put this information, yada, 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 right here. So I did this little squiggly line to imply about, kind of like approximate you do in math, but I just have one tilde there. So about 97% of all the water we have is in the oceans. The second thing I want you to write down is about 1.7% is in the groundwater, in the actual physical ground. About 1.7%, that should be percent symbol, so write percent there. About 1.7% is in the ice. And that's not counting permafrost there. And then less than 1%, actually much, much less than 1%, of all of that water that's available is directly available for human use. So when we say less than 1%, we're actually not talking about all of the water on Earth. We're talking about some of this water that's groundwater that we have access to that's actually not polluted. So this number here is representing the clean, fresh water that's safe for human consumption, that's safe to put on our crops, that's safe to give to our livestock. So less than 1% of all the water on Earth is directly available for human use. And so the take-home message is that we need to take care of our water resources. There are a lot of places in the world right now that lack clean water, that lack a lot of access to fresh water. And those places in the world, a lot of places in Africa right now, close to the Middle East, a lot of those places are in just unrest, and they're in war, and they're going after other countries and other resources because they don't have the water they need to be able to make a living, to be able to grow crops and feed their people. So it's very important on our planet to take the water that we have, keep it fresh and clean away from pollution so that we can continue recycling and using that water all the time. All right, so let's take some notes on water properties. This is what you focused on when you did your water properties lab, or if you didn't do it, will do in our water properties lab. So water is an essential to all life as we know it here on our planet. Water is so useful because it holds on to heat energy. It dissolves many different things inside the water, making it available for animals and things to take up, and plants. And an interesting thing about water is it floats when it's solid, and you're like, duh, ice floats. That's not interesting, but we'll talk about that in a bit and why it is actually so amazing. And it can also move against the force of gravity up into plants and allows plants to just soak up water just because water has these weird, strange properties that allows it to be attracted to the inside of plants. We'll actually call that capillary action, but we'll talk about that in a minute. So let's start with the first property of water. Now this is water properties. It is mimicked in your notes. You should see that right here on page 16 where it says water properties, and then it has a blank. That's where you're going to write universal solvent. So write this word right here, universal solvent. You're going to put that right here at the top of your notes, right there. So the universal solvent is where water can dissolve many things because of its polar property. We briefly talked about polar property when we introduced it when we were talking about chemistry at the beginning of the year. And we're going to define it again here. But when we say water is a universal solvent, basically we just mean it can dissolve a lot of different things. We can put a lot of things inside of water and have it actually just dissolve and be suspended in the water column evenly over the water. Things like Kool-Aid, salt, sugar, many different substances, minerals can be dissolved in the water and float around in the water column. So water's polar property. We talked about before that water's polar property, and I would not write this last little part right here if I were you. This right here. So don't just copy everything down word for word, even though you're not listening to me and you're just rambling. You're scrambling to write all of this down anyway. But water's polar property, water is slightly negative on the oxygen side and slightly positive on the hydrogen side. That's what gives it its polar property. Polar because it has polar opposites, or poles, as you guys learned about, like kind of like in magnets as well. It's not magnetic, but it's a little bit different. But it does have a slightly positive charge on one side and a slightly negative charge on the other side. This allows it to have an attractive properties, allowing it to be attracted to other things in the world. And we'll talk about it in detail in just a minute. Pause the video if you need more time to write this down. All right, so what we're going to do is we are going to create a diagram of what this kind of looks like in your notes. So right here, you have this code to tell us what things are. So right here, this is what a diagram looks like of the table salt, of sodium chloride. This is the salt that you eat when you are putting it on your food. Not all salts are edible. Don't eat any salt that you find. All right, and then we have the water molecule here. Often I like to call this the Mickey Mouse molecule because it's got the Mickey Mouse ears and then the Mickey Mouse head. So what we're going to do is we're going to draw that diagram, this diagram right. So we're going to go ahead and draw this diagram into our notes. And we're going to start doing that by drawing this sodium and chlorine. We're going to draw those ions into our stuff here. So I'm going to pull up my little drawy thingy. Okay, go ahead and grab a circle. We're going to draw a sodium ion right here. And the chlorine ion is actually quite a bit bigger than the sodium ion. So we're going to draw that one a little bit bigger. Okay, so I'm going to color this a color just so I can see that they're different things. Oops, that's a circle. I'm going to color these in just real quick. You don't have to color them. If you want your life to be sad without color and devoid of happiness, you can leave yours black and white. That's totally fine. All right, now I'm going to grab a blue, and I'm going to color my chlorine one blue. Expertly colored. Oh my gosh, that's so wonderful. Great. Okay. Now I'm going to label this my sodium, this yellow one. I'm going to label this my sodium ion. And I'll know it's an ion, and I'll know it's sodium because I'm going to use the chemical formula for sodium, which is Na. And I'm going to use that plus symbol. It actually has one positive charge. I'm going to use a plus symbol to represent that it is an ion with a positive charge, because we know it's an ion because we see the charge up here. All right, here, this is my chlorine atom. Chlorine is going to be represented with a capital C, lowercase l. And because it's an ion, it's a negative ion, so I'm going to represent that with a negative symbol up here. All right, so I've got my positive sodium ion, and I've got my negative chlorine ion right there. So what's actually happened is my water molecule with its slightly negative oxygen side and my slightly positive side has gone over to this salt crystal, which was more atoms in this, but it's gone to my salt crystal, and it's this pull from this negative and positive charge on the water molecule is stronger than the ionic bond that was held between the sodium and chlorine ion. So it actually splits these apart, even though they really just want to be together. It splits them apart, and it pushes them and separates them from each other, keeping them from one another. So we're going to go ahead and represent that with the water molecules. It looks, again, like this. So it's going to be all these water molecules surrounding our sodium and chlorine ion. So what we're going to do is go ahead and make yourself a few circles. Right here, the positive part of the water molecule is going to be attracted to this chlorine because it is negative. So I'm going to make a few red circles to represent my hydrogens here. I'm just going to put a few of them so it doesn't take us forever to draw this on here. But I'm going to have a few of these. So I'm going to draw, I'm going to draw 8 in total. These are my positively charged side of my water molecule. Again, my water molecule is a neutral atom. It is not a charged particle. It is not an ion because of the fact that it has as much negative charge as it has positive charge, but it's a little not equally weighted. I'm going to go ahead and make my Mickey Mouse molecule here. Ooh, some are better than others. Sorry. So those are going to be surrounding that chlorine, keeping away from its love of its life, the sodium ion. All right, now we're going to have that opposite effect here. Over here, the sodium, the water molecule's negative part, is much more attracted to the positive sodium. So it's going to keep its negative ends facing it at all times, keeping it separated from its level of life. Chlorine over there. Wow, these are great molecules I'm drawing. So here we got the negative oxygen, and then let's go ahead and draw our Mickey Mouse ears on our water molecule facing outward. Now, when evaporation processes happen, that's going to be when the water molecule has enough energy where it's escaping into a gas form, and it's leaving this beautiful liquid state. And there's not going to be enough of these to actually keep the sodium and chlorine apart. So what happens is as the water evaporates out of the glass, you'll see these sodium ions and these chloride ions, they will actually rejoin with one another and become a salt crystal once again, just like they were meant to be all along. Okay. Let's go ahead and talk why being a universal solvent matters and why we care at all. So we're going to write this down here in our notes, right where it says salt dissolved in liquid water suspended as ions, and then underneath that it says why water being a universal solvent is important. Why do we care? All right, so why this is important, these three things. This is what I want you to write down on those 3 bullets list that I showed you. Number 1, it breaks down minerals in rocks, then transports them in streams, which you're like, who cares? Why do I care? All of the minerals and stuff we have on this earth originally comes from the rock of the planet. So when rainwater actually hits the rock, it will dissolve because of this polar property and because sometimes it's slightly acidic. Okay, all the time it's slightly acidic, but that just helps. Mostly it's water doing the work. But it will actually interact with the rock itself and release minerals that plants can't get out of the rock, that fish can't get out of the rock by themselves. And it puts it into the water, dissolved into the water, so that plants and animals can take it up. This process of rainwater hitting rocks also creates soil. I don't know if you know this, but soil doesn't just happen on the earth just because it exists. Volcanoes and other processes will create rocks. And then when water rains down on it, it chemically alters the rock and changes some of those minerals into soil particles. And then also, if we talk about inside of our body, when you eat food, because water can dissolve many different substances, it allows it to take those substances into your bloodstream, transport it to different cells in your body, and have your food, instead of it just being food, dissolve substances that the cell can take in and either use for energy or use for vitamins or use for minerals that the body needs to survive. And water makes a lot of that possible. All right, so the next property here is adhesion and cohesion. So we're going to start with cohesion. You're going to write that right here under adhesion, cohesion on this line. This is for cohesion. And I'm going to write the definition here. And then we're also going to write draw a little bit of a diagram. So I would write the definition over here, yada, 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 and then put my diagram right here. But you can do a definition and then diagram squatty down here if you want. It doesn't really matter. They're your notes. You're the creator. You do you. All right. So here we have cohesion. Write that word cohesion. See the pencil symbol? Water's ability to weakly bond to other water molecules through hydrogen bonding. So cohesion, this prefix co means like together, to work together, to combine. So we have cohesion, meaning water's ability to weakly bond to other molecules through hydrogen bonding. We're going to go ahead and draw ourselves a diagram of that. Here, and I'm going to draw it with you with my expert drawing skills. We actually don't need to put in here that it's a covalent bond, so we're going to ignore that a little bit. We're actually going to ignore this whole water molecule over here. But there are strong covalent bonds holding this water molecule together between the atoms of the water molecule. But this is the part I want you to draw. So let's go ahead and draw our Mickey Mouse molecule. We've got oxygen here. And make sure you label that O for oxygen, so we know that that is oxygen. And then we're going to go ahead and draw ourselves some hydrogen atoms. And then we're going to represent their bond, their strong covalent bond here, with a line. I'm actually going to make it red so you can see what I'm doing here. So we're going to go ahead and make that line. So we have this water molecule and indicate that these are hydrogen with a capital H because that is the chemical symbol for hydrogen, our friend. All right, now let's go ahead and represent this bond between molecules with a dashed line. And then that's connecting it to our other water molecule here. Let's go ahead and draw our Mickey Mouse molecule here, indicating the O there, and drawing our line, our bond to our hydrogen molecules. Or, I mean, our hydrogen atoms, sorry. Use the proper terms here. All right, let's make sure we indicate those H's again, those capital H's to represent hydrogen. Here we go, hydrogen. All right, and now our diagram is just a pretty picture, unless, of course, we put a label on it. So let's draw a line that exists between this little dashed line that's representing our bond here, and let's label that, like it says here, with the words hydrogen, hydrogen bond. Wow, that is super small. I'm going to make that bigger. So label that with the words hydrogen bond. All right, everybody get that written down. Pause until you've got that done. Whoa, rewind. Okay. Our next property is adhesion. You're going to put that down here on this second blank here with the colon. So adhesion is going to go right there in your notes. So adhesion is water's ability to be attracted to other substances. So this would be a good example here of water sticking to other things. Like it goes into your shirt and soaks in because it's attracted to the actual molecules in your shirt. Or it makes your hair wet. Pause the video until you get this written down. Here's a good example of how adhesion and cohesion are at work. So here, this is an example of adhesion. This is two different substances. This one is water. And the second substance over here is actually mercury. They're both in a test tube. Now, mercury has a stronger pull to itself than it does to anything around it. And here, the water has a weak pull to itself, but it also has a weak pull to the glass. So if you notice here, water is slightly climbing the glass here, and here is most noticeable. But we actually have this whole, what we call the meniscus. You might have heard of that in 7th grade or 8th grade, where the water looks like it's kind of not level in the substance. Now, water self-levels all the time when it's not attracting to other things, but in a small container, it can tend to climb up the side of that container, and that's what we're seeing when they're seeing this dip here, is we're seeing the water actually climbing the sides of the glass and sort of rising up the sides of the glass. Now, if we had a smaller test tube, one that was really small, we'd see this much more exaggerated. This action right here can pull water molecules up inside of a plant, and I'll show you that in just a moment, a diagram of that, what that looks like. But this action is really actually super cool and essential for life on planet. Now here is a wacky picture. This one's awesome. So this is showing cohesion, water's ability to bond to itself. So this swimmer here is coming up out of the water, and this photographer has taken a amazingly timed photo at the instant where the water molecules have still not broken yet, and this person is coming out of the water, but the water all is still stuck to itself. It's still cohesing, if that's a word, to itself, and not broken yet. So this person's not quite out of the water. So you can see how the water is holding on to itself, and any moment now after this photograph was taken, the water will have broken its bonds and allow the person to surface. Some more examples of this kind of drops is in dewdrops. You can definitely see how water cohesively beads up on itself. It's making these little drops all over the flower instead of spreading out. And it's also attracted the flower a little bit with adhesion, so it's stuck to the petals instead of just rolling off with the force of gravity and falling off the edge of this flower petal. So it's not only attracted to itself, but it's also attracted to the flower petal itself. All right, now I said before that cohesion and adhesion work together inside plants, and that process is actually called capillary action. Here are some celery. Celery is great for this because it's basically got like long tubes inside of it. I'm not going to say the technical terms for those tubes, but they're going to make the water flow up inside of the plant and reach out and come out towards the leaves. Now, this is shown really well with food coloring. You might have done this experiment when you were in elementary, but basically it's got food coloring in the water to show this movement of the water up, because the water will actually evaporate out of the leaves, but the color doesn't actually evaporate out of the leaves, and so it gets stuck in the plant, and it gets actually as a toxin or poison in the plant, but it looks pretty cool in the experiment. So it'll actually suck up these colors, and the water will move up against the force of gravity with adhesion, meaning it's sticking to the inside of the plant cells and moving up slowly through the plant, and cohesion, meaning the water molecules want to stick with each other, so they'll pull up inside the plant, being attracted to the plant, and the water molecules themselves will help pull each other up inside the plant against the force of gravity. Adhesion and cohesion important to life. So cohesion causes surface tension. That's that thing that when you do a belly flop in the water, you feel that pain where the water doesn't really want to split out of the way, but eventually it forces you through it, and it feels like someone slapped your entire body with a giant, massive hand. But surface tension also allows bugs to stand on the water, which is kind of cool because then they don't drown or anything. They can be on the water. They can drink the water beyond the surface without actually sinking. Adhesion and cohesion work together to create capillary action. Capillary action is that movement of a liquid against the force of gravity in a small space, because the adhesion makes it attracted to whatever is the cells or the inside of a container, or even in the ground surface, allowing groundwater to move upward towards the soils. Capillary action moves water through a plant, was extremely important to life here on Earth. And then our last one here is cohesion allows water droplets to form in cloud formation. Also dewdrops and all that kind of stuff. But if we didn't have that cohesive property of water, if water didn't have that cohesive property, clouds wouldn't even form. We wouldn't get droplets. We wouldn't have this moisture in the air eventually condensing and growing larger and larger until they're large enough to fall as raindrops. Without that, we would never actually have rain on the planet. The next property of water is the density of water at different states of matter. So there, the only thing you need to write is the blue stuff right here on that blank. Right here, you're going to write density of water at different states of matter. Just density of water. That's all you're writing there. Write that down, and then let's talk about it. All right, this might not seem like a miraculous thing to you, but I'm going to tell you something about water that maybe you don't know. Okay, you know this. When water turns into the solid form, it floats as ice. Y'all know this. Y'all have been outside. You've seen ice floating on ponds. You've seen snow floating in melt water. You've seen ice cubes floating in your drink. You've all experienced this. And you're like, that's not amazing. That's stupid. You're being dumb, Mrs. Grether. But here's what is amazing. Remember back in at school when you learned about different phase changes, right? We learned that when molecules are heated up, they're getting a lot of energy. They're moving around. They're bouncing around. They're spreading out, right? And so when they go from being a frozen form, that's our solid, to being a liquid, to being a gas, the molecules are physically spreading out. They're taking up more space. They're being less dense. So we start with a rock. It heats up enough where the molecules no longer are stuck in this rigid form and they can move around and they can be a liquid. And then we heat them up enough and they get really crazy, and instead of bonding to one another in this liquid, they actually break their own bonds and they will go around as separate molecules floating around as a gas that we can breathe, and hopefully it's safe gas we can breathe. But it's just gas that is in the air because they have so much energy that they're really spread out. Well, when something is really spread out, it's less dense. When things are less dense, they float. Like the air floating on the earth and floating on the water, or the water floating above the rock, right on the rock on the planet. Or like wood floating on water. So things that are less dense will tend to float. And so when you have all these different forms of substances, almost all substances on the planet, when they go from gas down to liquid, they become more dense. When they go from liquid to solid, they become even more dense. So if you took a rock and you turned it into liquid rock, and you threw a rock in there, it would eventually sink to the bottom because it's solid. It doesn't float like an ice cube, but water does. Water does float, which is actually pretty amazing. Why this is so amazing is this picture right here. We're looking at winter. I don't know where. Let's pretend it's Wisconsin. Sure. We're looking at a lake, and the lake is completely frozen over, and we've got this layer of ice. But because ice floats, it is creating an insulating layer of ice that keeps this frigid, really cold, maybe minus 30-degree weather away from all the organisms that live beneath this ice. This ice keeps the water below only at just above freezing, just above the temperature for life to survive the entire winter and then move into spring, summer, and then return back to fall. So this ice being able to float is actually protected life on our planet from that winter frost and every aquatic habitat that we have pretty much on the planet. If ice sank when it froze to its solid form, we would have the air cooling down that water, that body of water, that lake, and then a layer of ice would sink to the bottom. And then we'd have another layer of ice that would get really, really cold, and it would sink to the bottom. And then eventually our entire lake system would fill 100% with ice, and all of the organisms in that aquatic system would perish. But since ice floats, that doesn't happen. We have ice rinks with and ice fishing where organisms can survive even in the coldest of winters. All right, so let's draw a diagram of water molecules and why they actually become less dense when they become ice crystals. I know you're going to have to suffer through my drawing again. You're welcome. Okay, so you have this in your notes. Doop, doop. Oop. So let's go ahead and switch down here to this page. So you got this exact thing on my screen in your notes on page 18. We're on page 18 here. So everybody get to page 18. So I'm actually going to draw what it looks like here on the right-hand side first. So everybody, let's draw our Mickey Mouse molecules. Let's go ahead and draw one there. I'm going to draw one over here. When water is in that liquid state, when it is what most of you will consider water, it has the ability to have so much energy that it can repel itself away, and it can get pushing itself really close to another water molecule. At this state, the heat energy that these water molecules have allow it to be bonded at really long bonds, and they can move, they stretch around, and so we can actually get these water molecules appearing much closer to one another than they ever would as a solid, and we'll explain why that is in just a second. Let's go ahead and just draw ourselves a few Mickey Mouse molecules showing these molecules moving around in random formations wherever they want. They can stretch, they can pull, they can break their bonds, they can remake bonds. They're going to be moving with such energy that they're just going to be kind of a chaotic, unorganized, bonded structure. So I'm just going to draw a few bonds here to show these links of bonds. And just for funsies, I'm going to draw one more water molecule. Fail. One more water molecule just to kind of show what's going on here. Gotta get my Mickey Mouse ears on. Alright, hopefully you all can make these diagrams a little bit faster than I can here. Alright, so in that water state, we can actually, the water molecules can get pretty tight and they can move apart. They're constantly in motion. They've got that energy motion. Now let's go back over here to our ice side. When we have our water molecule, now this one, we actually need to make sure we put these in specific formations. So we're going to have to pay attention to what we're doing. So everybody draw it just like me. I'm going to go ahead and make this easy first. We're going to draw this water molecule, how it forms in the ice. And I'm going to explain why that is. So when water starts to get cold, about 4 degrees Celsius, this is when it is actually the most dense, where the water molecules are so cold that they can't push on each other anymore. They're not crazy, they're not wild, they're not moving away from each other as far apart as they can anymore, because they're really cold, and so they don't have the energy to bounce off one another anymore, and they start getting really, really close. But once it gets colder than 4 degrees Celsius, an amazing thing happens with the water molecule, and it has to do with hydrogen bonds again. That's why this says hydrogen bond. When it gets super duper cold, the hydrogen bonds will take over, and they will force the water molecules to be in a perfect formation. So let's go ahead and draw ourselves water molecule. Because of its chemical makeup, will form in a hexagonal pattern. I'm trying to draw these perfect, but it's not exactly easy on my trackpad. Alright, so let's go ahead and draw ourselves 6 of these oxygen atoms. Not the best hexagon I've ever drawn in my life. Alright, so because the heat energy is so low, the bonding from these hydrogen bonds will take over. Now we're going to draw this one atom at a time to make sure we got this right. So here on your oxygen atom, to draw a hydrogen atom that's basically facing your next water molecule. And we're going to do that all the way around the whole circle so that we can get this pattern correctly drawn. Let's go ahead, just make your little hydrogen atom facing that molecule next to you. Now remember, this is happening because these hydrogen atoms have a slightly positive charge and this oxygen has a slightly negative charge. So all of the water molecules will turn and make these hexagonal structures. This is why snowflakes always form in these patterns, these beautiful patterns that they have. All right, now we're going to go ahead and take that other ear of Mickey Mouse and we're going to put it on the opposite side of our water molecules. Now these will all go and form patterns off of this structure, this base structure. Wow, these are really terrible Mickey Mouse ears, but we'll pretend that they're good. And now let's go ahead and draw our hydrogen bonds. So we can draw these hydrogen bonds from the hydrogen going to our oxygen, and we're going to go ahead and do that on every single one, connecting our water molecules one bond at a time. These all represent hydrogen bonds. All right, so right there, not the most perfect hexagon I've ever made, but nature, most things aren't perfect, so I guess it's representative. But you can see here, this is why it becomes less dense. See this space. This space is not filled in with air. A lot of people think that just, things between atoms or molecules is just air, but it's not. It's just empty space. So because this molecule, the hydrogen bonds will take over in the lack of energy, heat energy that it had in this liquid state, we end up having so much more space here in every section of this water molecule that ice becomes less dense as this solid state as it does in its energetic liquid state. Pause the video if you haven't had time to draw that just yet. Make sure it's in your notes. All right, so why water's solid density matters. We kind of already wrote this down, but we're going to put that right here on this part of your notes here where it says why water's solid density matters, and you have two bulleted parts on your bulleted list. So the first reason why it matters is layers of ice float in lakes and ponds, protecting life from the cold. Now our second reason is that ice freeze and thaw cycles, so ice freeze and thaw cycles, help to circulate matter and energy in deep ocean currents. We're going to talk more in depth about that when we talk about ocean currents, but I've been talking about how your experimentation final for the term is going to coming up soon. We're actually going to do an experiment on ice freeze and thaw cycles, and that is what your final is going to be on. So you're actually going to watch this in action in a small model form that we're going to create in the classroom, and you're going to be able to be awesome on that assessment. But yeah, when ice freezes and thaws, because it's more dense as that liquid, when it melts as ice, it'll actually send really, really cold water, super cold water, down to the bottom of the ocean and bring oxygen with it and push any kind of nutrients that are sitting there at the bottom of the ocean and move it along in these circulation patterns. And it's really, really super cool. Sorry, if you weren't done writing that, pause the video and finish writing that. All right, high specific heat value. So water has something called a high specific heat value. Everything has a specific heat value. It's not like water is the only thing that has a specific heat value. Everything has a specific heat value. Every chemical on the planet. But that is just, the specific heat is just the amount of energy it takes to raise 1 gram of something a whole degree Celsius or Kelvin. Either way, doesn't matter. They're the same-ish. So basically that means how much energy does it take to put into a substance to raise its actual temperature? Now, that second thing about high specific heat value that I want you to know is that substances with low specific heat value, so something with a low specific heat value, is going to transfer heat very quickly. So that blue word is all you're going to write here. So quickly, they heat up fast and they cool down fast. So, for example, rocks can get super hot during the day, but they don't hold on to their heat for very long. So even though they heat up really, really fast, they're actually going to release their heat really fast too. Anything that heats fast cools fast as well. Water definitely doesn't do that. Water, because it has that high specific heat value, it retains heat for much, much longer. So here down the bottom one, the third one, says water has a very high specific heat value, which means it will absorb a lot of energy, but it also means it's going to hold on to that energy for longer. So when you go to the beach during the day, the sand is really, really super hot because it heats up super, super fast. But then when you go into the lake, that lake feels super cold or super, super cool. But the sun's been shining on both of them for the same amount of time. The sun's had the same amount of time to heat up the sand as it has the water, but because they absorb energy differently, water absorbs a lot of energy, but it doesn't use all of it for heat, it's going to be a lot different. But what's important and cool about water, besides it being cool because of temperature, is that when the night comes, that sand gives off its heat pretty readily. It gets pretty cool. But the water still has a lot of heat left over from that day. And when the sun is down and when it's nighttime, water will dispense that heat throughout the night, which helps keep things really warm, or moderate is what we want to say, moderates the climate near large bodies of water. It helps keep places from being a large extreme. So, for example, here in Utah, if we didn't have the lake out where we have it, our days would be a lot hotter and our nights would be a lot colder because we would have more ground surface that would heat up faster throughout the day, and then the heat would be given off very readily at night, and we'd see more extreme temperatures than we see now. So why water's high specific heat value matters. That is here in your notes, yada, yada, yada. We already wrote all that, yada, yada, yada. Go to page 19. Why water's high specific heat value matters. Bullet 1, 2, 3, and 4. So why water's high specific heat value matters? Because water helps to regulate organisms' body temperature. So water doesn't change temperature very fast. So you go outside when it's cold, you don't freeze because a lot of your body, anywhere from 55 to 70%, depending on who you are and what time of day and how much you've had to drink, a lot of you is water that helps keep you warm when you go from one extreme to another. And it also helps you cool. If you go outside when it's 112 degrees outside, I used to live in Phoenix, Arizona, your body doesn't instantly die, it doesn't instantly heat up because you have water in you that takes a long time to slowly raise its temperature. Like I already mentioned, water can also moderate climates. It reduces temperature fluctuations. So it helps reduce temperatures during the daytime and it helps raise temperatures during the nighttime. Water can transfer heat energy from the equator to the poles. So we'll see that when we look at ocean currents. We actually see water moving heat temperature from the equator up towards the poles in giant circulation currents we call gyres. And then water can also slow heat's escape to space by water vapor existing in our atmosphere as our major greenhouse gas. Pause the video until you get all of those written down. All right, we actually did the properties of water exploratory lab first. So that's the lab that you guys already did when you worked with cohesion and you dropped the water droplets on there and saw how they beat it up and all that jazz. So we're actually going to skip this slide. All right, that brings us to our next topic, which is going to be, I think, Earth's atmospheric energy or ocean currents. One of those two. I don't remember. I think it's Earth's atmospheric energy. And we're going to talk about that next time.